Welcome to the first lecture of Module 6 of this course called Game Theory and Economics. So, this is the last module that we shall have in this course. So, before we start this module, let me just take you through what we have discussed in the previous module. And what we have discussed in the previous module is basically we have discussed extensive games, the theory of the extensive games, how they are defined, and what are the solution concepts. We have talked about two solution concepts. One is Nash equilibrium in the case of extensive games, and also subgame perfect equilibrium, because we have seen that the idea of Nash equilibrium may not be robust in case of extensive game with perfect information. And we have also seen one particular way of finding the subgame perfect equilibrium in extensive game of perfect information, which is called, this method is called the method of backward induction. What we propose to do in this last module, which will consist of only 2 lectures, is to look at some of the well-known illustrations, some of the well-known applications of extensive game, and how we solve those games and how our solution helps us to predict real life events. But before we start this last module, what we propose to do is that just finish one last exercise that we have been doing in the previous lecture, which is of course related to extensive game with perfect information and the application of backward induction. So, let us finish that exercise first, and then we shall start with this last the topics of this last module. So, this was the exercise. Choosing heterogeneous objects. 2 people choose k objects in turn, where k is greater than 2. First, player 1 picks up an object, then player 2 picks up one. In the third round, player 1 gets to move, etc., etc. So, these 2 players are alternatively choosing their objects from a collection of k objects. Preferences of the players are different, so they are not ranking the objects in the same manner. No player is indifferent between any 2 objects, so there is no indifference between the objects. If each player evaluates a set of objects according to the sum of the values she assigns to the objects in the set. So, if a player has selected k number of objects, or suppose n number of objects, then the total payoff that player is getting from this n number of objects is the sum total of individual payoffs from this n objects. Let xk denotes the object least liked by the player who does not choose the object in stage k. Let xk minus 1 denotes the object among the objects except xk least preferred by the player who does not choose, this should be choose, who does not choose in the stage k minus 1. This way we can denote all the k objects by xs, show that there may not be any subgame perfect equilibrium in which player 1 chooses her favorite object in the first round for k is equal to 3. Also show that if k is equal to 3, the game has a subgame perfect equilibrium in which for each j going from 1 to k, the object xj is chosen in stage j. So, there are 2 parts to this exercise. The first part is saying the following, that suppose k is equal to 3. So, there are 3 objects. Then there may not be any subgame perfect equilibrium where player 1 chooses her favorite object in the first round itself. So, I might like a particular object of the 3 objects, a particular object might be my favorite, but I might not pick that up in the first round in the subgame perfect equilibrium. Now, how that can happen? So, this is what we need to show. So, let us take the following preference pattern. I just have to construct an example. There are only two players, player 1 and player 2. Suppose this is the preference of player 1 and this is the preference of player 2, and suppose these are the scores. So, scores are nothing but the payoffs from the objects that these players are deriving. So, if player 1 gets object A, he gets 3, if he gets B, he gets 2, and if he gets C, he gets 1, like that for player 2. Now, here in this case of preferences, suppose player 1 does indeed pick up A in the first round. So, round 1, remember in round 1 player 1 gets to move. So, suppose he picks up A, then we have round 2. Now, A has gone, it is no longer there in the choice set. Then what should 2 do in round 2, because it is now player 2's turn to move. Player 2 here obviously will choose between B and C, and B is preferred by him. So, he will pick up B, and therefore, in round 3 only C is remained, which will go to player 1. And so, in this case what is the total payoff of player 1? It is payoff from A, which is 3, payoff from C, which is 1, 4, and what is the payoff of player 2? It is 2. So, this is one outcome, but the point is that this is not subgame perfect equilibrium here. Why is that so? Remember, if we want to find out the subgame perfect equilibrium, one fruitful way to do that is to start from the end of the game. Here the end of the game is round 3, and whatever object remains in round 3, player 1 picks that up. Now, player 1 knows the preference pattern of player 2, and player 1 knows that this object A is least liked by player 2. So, player 1 can figure out that in stage 2, when player 2 moves and picks up an object, he will never pick up A, because A is least liked by him. So, player 1 is guaranteed of A in round 3. Even if player 1 does not pick up A in round 1, he is sure that this A will be for him in round 3. In that case, player 1 need not pick up A in the first round, which he is doing right now. He can do better. So, what could be the better? A will not be picked up by player 1. So, A has gone out of this question. Between B and C, for player 1, B is better. So, the alternative, which is the subgame perfect equilibrium, is the following. In round 1, player 1 is picking up B. So, B has gone out of the question. In round 2, only A and C are remaining, and we know for player 2 C is better. So, C is picked up by player 2, and in round 3 player 1 is left with A. So, this is the subgame perfect equilibrium of this particular preference pattern and this game. In this case, player 1 is getting how much? He is getting A and B, which means 3 and 2, which is 5, and player 2 is getting C, which is 2 2, sorry, in the previous case player 2 was getting B, which is 3. So, this is subgame perfect equilibrium, where player 1 is basically calculating from the end of the game. He is looking at the game and introspecting, and he is finding that in stage 3 is assured of A. So, he need not pick up A in the first round, and therefore, he picks up B in the first round, which means that he is not picking up his favorite object in the first round, and which is what we needed to show. There is another part of this question also show that if k is equal to 3, the game has a subgame perfect equilibrium in which for each j going from 1 to k, the object xj is chosen in stage j. So, xj, j could be 1, 2, 3. Remember, here there are 3 k's, k is equal to 3. So, xj is picked up in round j. So, that is what we need to show in subgame perfect equilibrium. And there are 3 x's, x1, x2 and x3. And how these x1, x2, x3 are defined? x3, so the last x, k, 3, k is equal to 3. X3 is the object least liked by the person who gets to pick up the objects in stage 3, who does not get to pick up the object in stage 3. Here, who is the player who does not get to pick up the object in round 3? It is player 2. So, player 2 dislikes x3 most, or rather player 2 likes x3 least. And how is x2 defined? After we are excluding x3, then is x1 and x2. X2 is that object which is least liked by player 1, because player 1 is not the player who is moving in round 2. So, x2 is least liked by player 1 between x1 and x2. x2 is least liked by player 1 between x1 and x2. And then we have x1. x1 is the rest, the object that is remaining between x1, x2 and x3. So, this is how x1, x2 and x3 are defined in this game in terms of preference of these two players. What we need to show is that in the subgame perfect equilibrium, in stage 1, in round 1, player 1 will pick up x1, in round 2 player 2 will pick up x2, and in round 3 player 3 will pick up x3. What is the proof? The strategy of the proof is just what we have done just before in the part 1 of the question. Player 1, when he introspects the game, he can immediately see that he need not pick up x3 in round 1, because x3 is least liked by player 2 of the 3 objects. So, if player 2 is given a choice, he will not pick up x3 in round 2. When player 2 gets to move, it is round 2, player 2 will never pick up x3. So, x3 is something player 1 is guaranteed to get in round 3. So, first conclusion that we can draw is player 1 will not pick up x3 in round 1. because he is assured of this x3 in round 3. So, he is to choose between x1 and x2, and between x1 and x2 player 1 likes x1 more, right. This is because of this x2 is least liked by player 1 between x1 and x2. So, between x1 and x2 player 1 likes x1 more. Therefore, if player 1 has to choose any object in round 1, he will choose x1. So, in round 1 player 1 chooses x1. Therefore, in round 2 player 1, now it is player 2 who is going to move. Player 2 has to choose between x2 and x3, and we know that player 2 dislikes x3 most. Therefore, he picks up x2 in round 2, and therefore, player 1 chooses x3 in round 3, or rather he is left with x3 which he picks up. So, this is the proof that in subgame perfect equilibrium that player 1 chooses x1 in period 1, player 2 chooses x2 in period 2, and player 1 again chooses x3 in period 3. And this result holds for any k which is greater than 2, not only for k is equal to 3. For k greater than 3 also this will hold. Now, let me start with now the module that we were supposed to start, which is module 6, and what we propose to do in this module is to take some well known illustrations of subgame perfect equilibrium and extensive game with perfect information. So, the first well known game is known as Ultimatum Game. So, what is the story here? The story, let me first tell you the story and then we shall write down the story in terms of game theoretic language. So, here there are two players who are involved and they want to divide a fixed sum of money, constant sum of money, suppose the value is C, between them. So, you can think of this as a pie which they want to divide between themselves. In stage 1, player 1 proposes a division of this pie or this amount of money C. So, what player 1 does is to say, it is to specify the value of x, where this value of x can take any value between 0 and C, and this x is supposed to go to player 2. So, what player 1 is essentially doing, he is proposing a division of C between x and C minus x. So, this x is offered to player 2 in stage 1. After that, player 2 decides whether to accept the offer or not. If he accepts the offer, then the offer basically stands. Basically, player 1 will get C minus x and player 2 will get x. But if player 2 rejects the offer, he does not accept the offer, then the players will get 0 each. Basically both the players will get 0. So this is the game. Now before we write down the game in terms of game theoretic language, some observations can be made. First is that here the number of actions that player 1 can take can be infinite. He can take any x between 0 and c, and this x could be a continuous variable. In fact, x is a continuous variable, we shall assume that. So that is one point, and second point is that here player 2 has some pressure, can use some pressure tactics on player 1, because he can threaten to reject the offer, in which case player 1 will get 0. So though player 1 has some advantage, it seems that he gets to make the offer, but player 2 also has some weapons with himself that he can reject the offer and thereby hand over 0 to player 1. So let me first write the game in terms of the 4 elements. So there are 2 players, 1 and 2. Terminal histories. Where x can take any value between 0 and c, it is a continuous variable. So it is not indivisible, it is a divisible thing. Units are divisible, and z could be yes or no. Yes means that player 2 is accepting the offer, and no means he is rejecting the offer. Player function after the history phi, that is after null history, it is player 1's turn to move, that is player 1 is the first mover, and after any x specified by player 1, player 2 gets to move. Preferences are represented by the payoffs that the players are getting at the end of the game. So here what are the preferences that I need to, the payoffs that I need to mention? First let me write down the payoff of player 1. So if this is the terminal history x and y, which means he is offering x and player 2 is accepting that, then player 1 will get c minus x, and in this case what is the payoff of player 2? It is x, and if the response is no, then player 1 gets 0, and same is the case for player 2. If he says no, then he himself is getting 0. So this is how the preferences are defined. and we can draw this game in terms of the game tree, the familiar game tree. This is the layer after the terminal history, and he can make a continuum of offers x's. So, let us take any particular x, suppose this is x, and after this x is offered, then player 2 gets to move. He can either accept the offer or reject. If he is accepting the offer, the payoffs are c minus x, x 0 0. So, this is the game. So, this is a game of perfect information. Player 2 is aware of player 1's action in the first round, and it is a sequential game, extensive game, we can see that. So, one need to find out what is the subgame perfect equilibrium, or what are the subgame perfect equilibria in this game. So, we again apply the idea of backward induction, that we start with the subgame of length 1, which is, there is just one subgame of length 1, and in this subgame look at the optimal action of player 2. Player 2 is to choose between x and 0. If he says yes, he is getting x. If he is saying no, he is getting 0. So, ideally he should choose y, that is yes, if x is positive, and if x is 0, then he is indifferent, player 2 is indifferent. Now, this is the strategy that player 1 will keep in mind when he decides his optimal action at the start of the game where he is moving first, that is at the start of this game, subgame of length 2, which is the entire game. Now, he ideally will like to minimize the x which is going to player 2, because if he minimizes the amount of money that goes to player 2, then his share is going to rise. It is a constant sum game. If you reduce the payoff of the other player, your payoff rises. Now, ideally he will like to give player 2 0. So, if x is equal to 0, his own payoff is maximum. However, if x is equal to 0, then there is a complication. The complication is something which I have mentioned just now, that if x is equal to 0, player 2 is indifferent between choosing y or n. So, he can choose either of these two strategies, and both strategies are optimal. These two strategies are the following. One is that accept with x greater than or equal to 0. So, it does not matter whether x is 0 or not, he is going to accept any offer. In this case, we are basically saying that if he is given the offer 0, he is going to accept that, because by rejecting that also he is getting 0. So, he is indifferent, so why not accept? So, this could be one strategy of his, of player 2, and the other optimal strategy of player 2 could be and reject if x is equal to 0. So, he is going to accept any offer if x is positive, but he is going to reject if x is equal to 0. Now, both of them are optimal for player 2 as we have just seen, but as far as player 1 is concerned, if the strategy is this one, accept any offer with x is positive or equal to 0, then player 1's optimal action with respect to this strategy is to offer 0. So, with respect to A, one's optimal strategy is to offer x equal to 0. So, player 1 offers 0, which by A is accepted by player 2, and that is the end of it. So, in this case we are indeed having a subgame perfect equilibrium. This is a subgame perfect equilibrium. But what happens if player 2 adopts the second strategy, which is also optimal for him, that he is going to accept any offer if x is positive and reject if x is equal to 0. If this is the strategy of player 2, then player 1 does not have any optimal strategy. This is because of the familiar reason that here the x could be the variable x could be a continuous variable. So, what player 2 is saying that if you accept me, if you offer me 0, I am going to reject that. So, one will like to give a positive x to player 2, but if one tries to give any positive x to player 2, there could be another x which is better for one. For example, suppose one offers x bar which is positive. So, I know that this is going to be accepted by player 2, but one has a more optimal strategy of offering x bar divided by 2, for example. In that case, player 2 is getting x bar divided by 2 and one is getting c minus x bar divided by 2, which is better, which is higher than c minus x bar. So, because of the familiar reason that we have a continuous variable, player 1 does not have an optimal strategy when player 2 is taking the strategy that he is going to accept only positive x's. Therefore, there is no subgame perfect equilibrium in this case. So, we have the unique subgame perfect equilibrium where player 1 offers x is equal to 0 in stage 1, player 2 player 2 strategy is to accept any x which is non-negative. So, and here the equilibrium payoff are C and 0. There is one is getting the entire pi and player 2 is getting nothing. So, this might sound and this might seem a little unusual, because if you remember, we started out by making the observation that player 2, though he is moving second, has some tactical advantage, because he can reject any offer and thereby punishing player 1. If player 1 plans to make any unequal offer which is not to the advantage of player 2. But what is driving this result, what is giving us this result of C0 payoff, is that here the players are concerned only about their own payoffs. So, it does not matter what the other player is getting. If my payoff is higher, then that is better for me. So, that is the result, that is the assumption which is driving the result, that even if player 1 gives the other player 0, the other player might accept that offer, because if he rejects the offer, he is again getting 0. So, by deviating, the other player is not better off, and if the other player is not better off, then we have this Nash equilibrium in this subgame, and therefore Nash equilibrium in every subgame, and therefore subgame perfect Nash equilibrium. So, this is the reason why we are getting this strange result. One more interesting observation is that this might not seem like a bargaining process, but it is indeed a bargaining which is going on here. There is a fixed value which is to be assigned to two players 1 and 2, and these two players are making just a one shot bargaining, in the sense that player 1 is making an offer, player 2 is accepting or rejecting, and there the game is ending. But we can generalize this process a little bit more by incorporating the following procedure, that after player 2 is rejecting an offer, it is not the case that they are getting 0 each, but then player 2 gets to make his own offer to player 1. So, that is that is stage 3. So, in stage 3, player 2 is going to make an offer after saying no, and after that maybe player 1 again says accept or reject, and then he makes his own offer if he says no. So, that way it can be seen, this process of ultimatum game can be extended and can be seen as a process of bargaining. And we have some very interesting models, if we have a bargaining models, interesting results in that model. But right now our focus is only on the simple ultimatum game. What we propose to do now is to look at some of the exercises related to this ultimatum game. So, let us take some exercises. So, this is one exercise. Find the values of x for which there is a Nash equilibrium of the ultimatum game in which person 1 offers x. So, we are talking about Nash equilibrium here. So, question is the following, that what are the values of x for which there is a Nash equilibrium where x is offered by player 1 to player 2. And our claim is the following, that there could be infinite number of x's. So, any x lying between 0 and c could be offered by player 1 in a Nash equilibrium. And how do I prove that? Basically, when we claim that any x, any particular x, for example, not all x's, for example, any particular x is a Nash equilibrium, I have to specify what are the strategies of the players which are supporting this Nash equilibrium. Because if you remember, in an extensive game, for any Nash equilibrium, I have to specify what are the strategies, and in particular what is the strategy profile which is basically justifying this Nash equilibrium. So, suppose we take any x lying between 0 and c, and suppose player 2 has the strategy to reject any offer where her share is less than x, and accept any offer where her share suppose this is the strategy of player 2. Now, if this is the strategy of player 2, and suppose player 1 strategy is offering x, then this is a Nash equilibrium, this combination of strategies of player 1 and player 2. Our claim is that this is a Nash equilibrium, and this is not very difficult to see. What player 2 is saying, that if you offer me less than x, I am going to reject that, and if you offer me is equal to x or more than x as my share, I am going to accept all those offers. And with respect to this, player 1 is offering player 2 x, and obviously in this case the outcome will be that player 2 will accept the offer. This is Nash equilibrium for the following reason, that given player 2 strategy, obviously player 1 is not going to give him more than x, because in that case his own payoff will go down. So, player 1's strategy is optimal. Player 2 strategy is optimal because he is saying that if you offer me less than x, I am going to reject that offer. Now, and player 1 is indeed offering him x. So, if player 1 had offered him less than x, then rejecting that offer would have been suboptimal for player 2, because by rejecting he is getting 0. By accepting any x which is positive, but less than this x which he is specifying in his strategy, he is getting some positive payoff. So, that is suboptimal, but that is outside the terminal history described by this strategy profile. So, therefore, it does not matter what he is specifying outside the terminal history. On the terminal history, his strategy is optimal, and that is what we need to know in case of Nash equilibrium, because we are not talking about subgame perfect Nash equilibrium here. So, any x the result is that any x which lies between 0 and x, 0 and c could be the x that is offered by player 1 to player 2 in a Nash equilibrium. Let us take another exercise. Find the subgame perfect equilibrium of the variant of the ultimatum game in which the amount of money is available in multiple of a cent. So, C is available in multiple of a cent. Cent is the smallest denominator. In Indian convention it could be paise. So, C is available in the multiple of paisa. In this case, does the result change in the ultimatum game? That is the question. And the answer is, in fact, it does, because if you remember, in the subgame perfect equilibrium, we said that player 2 has two optimal strategies. One is that he is saying that I am going to reject any offer. This was the strategy B. Reject an offer where x is 0 and accept offers where x is positive. All right. This could be an optimal strategy for player 2. He is saying that if you give me positive things, positive share, only then I am going to accept that, because if you give me 0, then I may as well reject that. If you give me, if I reject that, I will get 0. If I accept that also, I will get 0. So, I am indifferent. So, I might as well reject an offer where x is 0. With respect to this strategy of player 2, player 1 did not have any best response if x was in continuous terms. But here what we are saying in this changed circumstances, we are saying that C has this nature that it is measured in terms of units which are not divisible, which are indivisible. In that case, player 1 now will have a optimal best response. So, with respect to this strategy, of 2, one's optimal right, because there is some minimum here. In the previous case, when x was continuous, there was no minimum value for x which is greater than 0. Here 1 is the minimum value of x. So, we have two subgame perfect equilibria in this case. One is offer 0. This is the strategy of player 1, and then after comma we have the strategy of player 2, accept any offer with x positive or 0. And there is this other subgame perfect equilibrium is offer So, this is the strategy of player 2. He is going to accept x's which are positive and he is going to reject any x which is 0. So, we have two subgame perfect equilibrium in this game. We can have some variations of ultimatum game, and we can talk about two kinds of variations. One is what is known as the dictator game. The dictator game differs from the ultimatum game only in that person 2 does not have the option to reject person 1's offer. So, here person 1, that is player 1, is offering some x to player 2 in stage 1. In stage 2, player 2 cannot reject that offer. So, that will be called a dictator game, because here player 1 is acting as the dictator, the other player does not have any power. And the other variation is called what is known as the impunity game. It is also a variation of the ultimatum game, only in that person 1's payoff when person 2 rejects any offer is c minus x rather than 0. So, if person 2 rejects any offer, it is not that person 1 is going to get 0, but he is going to get c minus x. So, it looks like the following: 1, he is making some offer x, and again here player 2 can say yes or no. If yes, the payoffs are these. If no, player 1's payoff remains c minus x, but player 2's payoff becomes 0. So, here it is called impunity game, because player 2, though he can say no, but in that no action player 1 is not getting 0, he is having some impunity, and that is why he is getting c minus x. So, by saying no, player 2 is in fact harming himself, not harming the other player. So, that is it. One interesting other variation of ultimatum game is what is known as the Holdup game. I shall just introduce this game here, and then we shall call it a day, and maybe we shall take this game up in the next lecture, the last lecture. Here the Holdup game, the story is the following: there are 3 stages here instead of 2 stages. So, first player 2 gets to move, then player 1 gets to move, and then again player 2 gets to move. Now, in 1 and this last 2 stages, the game is just like the ultimatum game as we have seen before. But in stage 1, what does player 2 do? Player 2 puts an effort in stage 1. And this effort could be high or low. If he puts high effort, then the size of the pie, that is C, is high, it is a big pie. If he puts low effort, then the size of the pie is also small. So, the size decreases. And after these 2 actions are taken, then only player 1 makes an offer, makes an offer to player 2. It could be from the big pie or from the small pie, and then only player 2 gets to accept or reject. So, that is the game. How many subgame perfect equilibria are there in the ultimatum game if C can be divided into smallest possible units? Which are they? So, try to remember the ultimatum game. First, player 1 makes an offer. Okay, he basically is deciding x such that this x is something which will go to player 2, and if x goes to player 2, player 1 will be left with C minus x. This is the case where if player 2 says yes, that he is accepting the offer. If player 2 says no, both the players are getting 0. So, this was the structure of the ultimatum game. We have to find out what are the subgame perfect equilibria here. Now, again using backward induction, okay, we know player 2 is going to maximize his payoff in this subgame of length 1. Now, if player 2 is going to maximize the subgame his payoff, as long as x is positive, player 2 is going to say yes, because if he says no, he is going to get 0. But remember, player 1 remember player 1 minimizes x, because if he minimizes x, his player 1's payoff rises. Now, if player 1 minimizes x, then to what extent he can reduce x? Player 1 can put x equal to 0. That is possible. Now, however, if player 1 puts x equal to 0, then 2 is indifferent between y and n. So, he can take two sorts of strategies. Both are optimal. One, accept any x greater than or equal to 0. Okay. This is optimal, because even if x is 0, the person is indifferent and he is accepting. This is optimal, and if obviously if x is positive, he is accepting that is also optimal. But there is another strategy, which is accept if x is positive and reject if x is 0. This is also optimal. Okay. Now, here is the problem. For 1, if 1 is the strategy of player 2, one's optimal action, optimal strategy is x is equal to 0, right? And so, this is subgame perfect equilibrium. Player 1 offers x is equal to 0 and player 2 accepts that given this strategy. But for 2, that is, if player 2 is saying I am going to accept only if x is positive, there is no optimal strategy of player 1. So, no subgame perfect equilibrium here. So, there is unique subgame perfect equilibrium where one strategy is x equal to 0, 2 strategy is accept if x is positive or 0. Okay. So, there is a unique subgame perfect equilibrium. If C is measured in terms of discrete units, then what are the subgame perfect equilibria? If smallest possible unit is 1, right. Then for strategy 2 of player 2, one's optimal strategy is x is equal to c minus 1. So now we have two subgame perfect equilibrium, right. One is x equal to 0 and x equal to 1. For x equal to 0, what is player 2 strategy? Accept if x is greater than equal to 0, accept if x is positive, reject if x equal to 0. Thank you.